Welcome to Brain Vision.
So we start with the wave function for a particle in a box, and we'll assume that it is a sign dependence, basically a sign function. And we're going to calculate the quantities that are needed for the uncertainties in the uncertainty principle, namely the mean or expectation values of x, x squared, p, and p squared. And so in doing so, this will allow us to get the uncertainties. And we'll see what happens when n approaches zero, basically when n is equal to zero. So we'll start with x, with its expectation value. And we'll see what happens basically in getting a contradiction for the uncertainty principle. So the expectation value is obtained by putting the operator x in the integral times, in this case, the square of the wave function. And we obtain the following integral, which you can obtain just by looking at a table of integrals. It's kind of a complicated integral. You can also do this integral with integration by parts. But this is the integral we obtain on the interval from 0 to L. And I simplify this further. In the next line, I'm going to go ahead and scroll down. And we'll basically just keep going and we'll get the final result. And we see that for the expectation value of x, it's really just L over 2, which is what we would expect for a particle in a box of length L. So on average, a particle is halfway along. It's somewhere in that interval, on average halfway. So now we'll go on and get the expectation value for x squared. So we just substitute in x squared inside the integral and multiply by the square of the wave function and integrate from 0 to L. And we get, again, another complicated integral, but we can use a table of integrals or use integration by parts, and we get the following. So notice in this integral that a lot of it will go away. You have the sign multiplying this quantity in parentheses involving x squared times L and L cubed. But because of the sign function, it's going to be 0 at x equal to 0 as well as x equal to L. And you'll know that because you have a 2 pi times n inside of the sign function. So automatically, those terms will vanish because they multiply by that sign function. And again, all of that is evaluated at 0 and L, but this greatly simplifies, and we have the following that comes about. And this is the final result we get. So we have L cubed over 6 minus L cubed times cosine 2 pi n over 4 pi squared divided by, or n squared in the denominator as well, multiplied by 2 over L. That simplifies to what we have for the final result. L squared over 3 minus L squared over 2 pi squared n squared. And we see that already, if n is equal to 0, we start to see something that's a bit questionable and a little bit suspicious. So we'll keep that in mind, and we'll go ahead and see what the uncertainty is for x, because now we can get that. So the uncertainty, once again, is the expectation value of x squared minus, well, it's really the square root of the expectation value of x squared minus the expectation value of x squared. And when you substitute in what we have, you get the following, which can be simplified somewhat. And here we see that again, we have n squared in a denominator, and on top of that, in a square root with a minus sign on it. So we can already see that we may run into trouble later. If we pull the n out, we still can have some difficulties later when n is equal to 0. And that's what we're going to be talking about once we have momentum expectation values taken care of. So now let's go ahead and move on to the momentum expectation values. So to calculate these, you're going to have a derivative of the function that's on the right-hand side inside the integral, like this. In this case, we have two sine functions. And this gives you a sine function multiplied by a cosine function, which when you integrate will give you a sine squared, as you'll see in this next step. And when we evaluate this from 0 to L, we obtain sine squared of n pi, because sine squared evaluated at 0 is obviously 0. But if we evaluate sine squared n pi x over L at L, that leaves us with sine squared of n pi. But n times pi is always going to be 0, even if n is equal to 0. So the expectation value of momentum is 0. That simply tells us that on the average, the momentum for a particle in a box is 0. And that's what we would expect. Now, let's go ahead and get the expectation value for the momentum squared. And here we take the second derivative of the wave function on the right-hand side in the integral. And so we're just taking the derivative of it twice, and we get the sign on the left times a factor with a negative sign on it times the sign again. We scroll down, and this evaluates to a positive constant that's proportional to n squared times an integral, which as we see is really just 1 because the wave function is normalized. This is the integral of the square of the wave function, which is 1. So we end up with the square, the expectation value of the square of the momentum operator being h bar squared pi squared n squared over L squared. And this, along with the average momentum being 0, allows us to get the uncertainty in the momentum. And there should be a square root right here. So we'll go ahead and place that. And we simply get for the uncertainty in the momentum h bar pi n over L, which is a fairly simple result. So we can now multiply the uncertainty in position and the uncertainty in the momentum to get the final result that we're looking for and compare this with what the uncertainty principle would normally tell us. And here's what we have. So we see that for values of n greater than 0, for non-zero values of n, we get a result that's reasonable. If you substitute n equal to 1, or 2, or 3, or 4, or keep going, you'll get values that satisfy the inequality for the uncertainty principle. If you substitute a value for 0 that's equal to 0, however, that's where you're going to see that there's the problem. So you end up actually with the following. You get I times h bar over the square root of 2. So it does violate the uncertainty principle because you have a purely imaginary number, and you can't have that in this inequality which depends solely on real numbers.